Hello everyone, welcome back. This time we're going to look at our composite objects. This is the last lesson in this sort of playlist here. And a composite object really is just a couple of the 3D objects we've looked at already, but combined. Right, because nothing in the real world really is just like one object or the other. Sometimes we got to think about the ones where they get combined together and you may have multiple. So we'll talk about both surface area, volume, and we'll talk about the differences between them. But the volume cases that we'll talk about first definitely are the easier ones to deal with compared to surface area. And again, down in the description, you'll find the blank copy of this document if you wanted to follow along, and the solutions as well, so you can have the full filled out version if you need that one as well. So let's deal with volume first. You can see right at the top it says our composite object really is just going to be an object comprised of two or more distinct objects. Now these ones only have two. Well, this one I should say only has two. I think one of the ones down below might have a couple more. But when we deal with volume, think about this idea. Imagine that you've got two water bottles, right? So if you think about what their shape might be, they would be cylinders as their 3D object. And if you were to put one of those cylinders on top of the other, right? One of those water bottles stacked on top of the other one, well, that's not going to change how much each water bottle can hold. Remember, volume is talking about the inside of that object. So when we deal with volume of these composite objects, if I could find the volume of each individual object, really all we're going to do is add them together. So at first I need to decide what objects we're working with. And in this first one, it looks like we've got a pyramid on the top. Okay, pyramid on the top. And it's sitting on top of a rectangular prism. Okay, so there's my two objects. So if I could find the volume of each of them independently, we're just going to add them together. So let's go find the volume of our pyramid. We'll do that one first. I want to organize this a lot better than I did last time. So let's do the volume of a pyramid. We'll do that part in this. We'll make a little chart here. So volume of a pyramid. And we'll do then the volume of the prism. Okay, and that'll be our rectangular prism. Let's see if we can make that a straight line. There we go. Looks like that. Okay, so our pyramid first. And if we remember what our formula for the volume of a pyramid is, as long as it's got a rectangular prism as the same size base, well, really it's going to be length times width times height, but divided by 3. 3 identical pyramids will fit inside that rectangular prism. So as long as I know the length, the width, and the height, I'll throw them in there, divide by 3, and away we go. And the dimensions that you can see are the same ones that are on that prism. So the base of our pyramid is going to be a 6.7 meters by 2.9. So we're going to have 6.7 by 2.9, and then the height of it. Well, there's two different heights we talked about, either the vertical height or the slanted height down the side of that pyramid. Now the slanted height we would say for surface area, so vertical height is going to be the one we're looking for, 2.1. So 2.1 meters. Divide by 3, and you can grab your calculator, put all that stuff in. I've kind of done that ahead of time to save us a little bit of time here. And that number works out to be 13.601 meters cubed. Units are important for volume, so meters cubed. We'll do the same thing, find the volume of the prism, and then we can combine them together. So the volume is length, width, height. And again, I just need those dimensions of that rectangular prism. So this time 6.7, 2.9, and well, I guess again 2.9. So that works out really nicely. So you keep it color coded. So we'll do 6.7, 2.9, 2.9, and our volume of that rectangular prism works out to be 56.347 meters cubed. So there we go. I've got the two volumes, one for the prism, one for the pyramid. Our very last step is to combine them. Really just add them together. So the total volume is going to be our 13.601 meters cubed plus 56.347 meters cubed for a total of 69.948 meters cubed. And if we were to round that to the nearest whole number, just to make it a little bit easier on ourselves, we're going to end up with 70 meters cubed. Now I know it didn't tell us where to round to here, so really we were free to decide where to do that. So 70 looks like a nice round number. So we can find them each individually, add them up at the end. Okay, volume is the easier case out of the two. Okay, we'll look at one more with volume before we talk about surface area. So we'll do both in this video here. If you want to try this one by yourself, now would be a good time to pause it, try it out, see what happens, and then continue on. And I'll do the full answer key here as well. So if you want to pause it, now would be a good time. Okay, let's take a look at how we would do this one. So first thing, you're going to decide what shapes, I keep saying shapes, what objects you're actually working with. And this time it looks like I've got a cylinder with what looks like half of a sphere on the top. So really that's a hemisphere. And again, if we can find the volume of them individually, then we'll add them up in the end. And your volume formula for a hemisphere is going to be, well, half of that of a full sphere. Okay, so the volume of your hemisphere. And again, we'll do that whole chart idea. Keep it nice and organized. So there we go, just like that. Got our, there we go, made it straight this time, perfect. So the volume of our hemisphere is going to be 2 pi r cubed over 3. A full sphere would then be 4 pi r cubed divided by 3, but I've only got half of it to deal with. So you can think about it two ways. You can find the volume of a full sphere, divide the answer by 2, but if I just cut the formula in half to begin with, well then I don't have to do that divide by 2. Essentially we're just doing it first. Either way works out the same. And the only dimension that you need for a hemisphere or a sphere really is the radius. So make sure that that picture tells you go to radius. This time I do, it's 18, so I know all I need to know. So we'll put all that stuff in. So 2 pi, and then in our brackets are 18 centimeters. That'll be our radius, so 18 cubed. Divide that whole thing by 3. And again, I've grabbed the numbers already. I've already typed them into my calculator. So volume equals 12214, so 12,214.5 centimeters cubed. Okay, there's what it should work out to be. And then we'll do the same thing, find the volume of our cylinder as well. So the volume of our cylinder, oops, I need me in there, cylinder. Well, the volume of the cylinder really is just the area of the base. Base is a circle, so pi r squared. And then we'll multiply by how tall it is. So multiply by height. This time I need 2 dimensions, a radius of the cylinder, height of the cylinder. Now the radius of the cylinder will be the exact same as the radius of that hemisphere because it's sitting directly on top of it. So 18 as a radius, 32 as our height. So we can throw all that stuff in there as well. So pi radius of 18, this time squared, and our height is 32. So our volume works out to be 32,572.03 centimeters cubed once again. Okay, there's our units for volume. And again, very last thing to do, we found each of the volumes of separately of those pieces. So we'll just combine to get our total. Okay, we're just going to combine for the total. Let's see if I can extend this a little bit. There we go. Different colors, but I'll do. So total volume. Well, we're just going to add those two numbers together. So 12,214.5 centimeters cubed plus 32,572.03 centimeters cubed for a total volume. Once they're added together, looks like it is 44,786.5 centimeters cubed. There is our total. Okay, adding them all up, really just those two individual pieces added together for a total of that 44,000 number. So volume is definitely the easier case out of the two, especially if you've done surface area of regular 3D objects. There's just more faces to think about for surface area. Volume's easier, you just deal with the inside. Now all that being said, well, I guess we got to deal with surface area now. So we'll do a couple. One is definitely more complex than the other one. And I'm going to actually scroll down and start with this one. Okay, it's a little bit easier to think about when we're going to talk about surface area. Okay, so there's these two examples on the bottom. We'll deal with surface area. Now, again, it's a composite object. Two parts to it. We've got looks like a square-based pyramid on the top, and I can tell that it's a square base because the shape underneath of it is a cube. Each of the lengths are 5, 5, 5, so all the sides are the same, which means the base of that pyramid is a square. So that's helpful, actually. It makes it a lot easier to find the area of that pyramid. Now, and the bottom shape is a cube. Now, the fact that there is a pyramid sitting on top of the cube does something for us. If this was a full pyramid, I'd have to find all 4 triangular faces, that lateral area, along with the base. But since the pyramid is on top of the cube, the base really is covered up. The base of the pyramid technically is not there. And if it's covering up one of the faces on the cube, well, that face isn't there as well. So there's actually 2 areas here that I have to take into account and actually take them out. So I don't want to include the base of the pyramid, and I don't want to include the top of the cube. Both of those things are overlapping and they're not exposed. So you can think about this by maybe grabbing a couple objects you've got near you. So I've got like my phone case, some glasses cleaner. If you put them on top of each other, well, the base of that glasses cleaner is a circle, but now it's covered. Imagine these are glued together and attached. Well, that circle is not actually there, and the exact same size circle is actually covered up on this phone case. So there's always going to be 2 when they overlap. So in this case, base of our pyramid, top of the cube. We got to deal with those and take them out, or don't even add them in the first place. Okay, that's the other way you can think about this. So let's go. Personally, what I like to do, find the full shapes, including the side that's not there, and then explicitly say what we're going to take out after. Okay, it makes it a little bit more, a little bit easier to see, and you can tell a lot more what it is you aren't including. So let's find the area of the cube first. And again, personal preference, but I like to do it finding the full thing, the full object. Alright, so there we go, area of our cube. So our surface area is going to be 6 multiplied by the side length squared, because all 6 sides are going to be the same. So if I can find one of them by doing the side length squared, we'll just multiply it by 6 for all 6. So 6 times 5 squared, well, that's really going to be 6 multiplied with 25, and that'll be 150. So if I include all 6 sides of the cube, each of them is 25, but since there's 6 of them, 150 in total. Now, one of those sides I'm going to have to take out. It's covered up by the pyramid, so we'll just keep that in mind. Okay, so area of our pyramid will come next. Area of the pyramid. And we'll split that up. Okay. Now, if it's a pyramid, I have to do the area of the base plus the area of the faces. And this time, those faces happen to be 4 triangles. Now, the base of the pyramid has the same dimensions as the cube, 5 by 5, right? Because they perfectly overlap. So our base is going to be 5 squared, because they're the same, plus those 4 faces, so 4 of them. Now if the face is a triangle, we're going to do base multiplied by height divided by 2. So we're going to have 5 times 4 over 2, 5 being the base of the triangle, 4 being the height of the triangle. Since we're talking about area, I need the slanted height, which I'm given. I didn't have to go solve for it. I actually knew it was 4. Okay, so I've got all the things I need. So we can grab a calculator, throw all that stuff in there, and we will end up with, this will work out to be 65 meters squared in total. Okay, so I know the surface area of the cube is 150, surface area of the pyramid 65. But now we got to talk about the areas that we need to, subtract, because we said that there's going to be some that overlap, so we're going to need to deal with those. So the areas that are not exposed, okay, the ones that are covered, the ones that aren't actually there. So the base of the pyramid, that's covered up. It's covered up by the top part of the cube, and the top of the cube is covered by the base of the pyramid. They overlap with each other. Okay, so the top of the cube. And usually what you'll notice is every time you find those sides that overlap, they're going to have the exact same measurements. So if you find one of them, double it and take out, well, the doubled version of it. You're going to have two of the same side that come out. Now it'll be a square, right? Side length squared, because we had a square base pyramid, we had a cube. So whatever I find the area of that one side, we're going to double it. So that side length happens to be 5. 5 squared is 25, so doubled should give us 50. Okay, so the area that we're going to need to subtract here is 50 meters squared. 25 from the pyramid, 25 from the cube. Okay, those two together make up that 50, one of each. So then we'll just do our total. So the total area, okay, it's going to be our 150 from the cube plus 65 from the pyramid minus 50 because, well, I've double counted to some sides now, right? I counted the part of the cube, I counted the part of the pyramid that aren't exposed. That's why we're going to take them out at the end. And our total volume then will work out to be 165. 165 meters squared. So surface area, you can see definitely more to think about because we've got to think about the pieces that are actually not exposed, right? The pieces that aren't actually there. Pretend this is one big solid object, right? The base and the top aren't there. Okay? And the reason why I wanted to start with this one is because there was less to think about. There was only one overlapping section. So if you want to give the one above a try, again, now would be a good time to probably pause it and try it out, because I'm going to do that full solution for you here as well. And maybe I'll erase that part. There we go. Okay, so again, surface area. And we'll do the same thing. So if you want to try it on your own, pause it first before we go do the answer here. So if we're going to look at this one, we're really going to have to decide what it is we're working with first. We've got some cylinders, okay, so 2 on either side, and they look like they're going to be the same. And you've got a skinnier cylinder in the middle. Now, where each of the cylinders attach to each other, there's going to be an overlapping section, one on each side. So now I've got 2 to think about. Let me just zoom in for a little bit here. Now, where the small cylinder attaches to the big one, really, if you think about it, it is just like talking about the end parts. So really, the circle on either side. And it just gets overlapped twice. So I'll do this in red, so maybe it's a little bit easier to see. And we'll imagine that we can see the other side of this. But there's going to be 2 circles on each side. One from the small cylinder, one from the big one from the small cylinder, one from the big one. But the same size of it will get overlapped twice. So where each time they overlap, you're going to have 2 circles for a total of 4 circles that we're going to need to take out. 4 circles to be subtracted. Each of them, the small ones. 2 from each side, left and right. Other than that, we're going to add all the other areas together. So again, I like to find the full areas first, figure out what I have to subtract, and then do that. It gives a nice routine how we could do this. So let's go find the area of the larger cylinders first. Okay, area, large cylinders. And I know I'm going to come all the way over there, so let's start building up our chart. Okay, so we'll do our large cylinders there first. And that's on a straight line. There we go. Okay. So a cylinder, again, we're doing area, not volume. Okay, so our surface area of one cylinder is going to be 2 pi r squared plus 2 pi r h. That'll be for one of them, but I've actually got 2. Okay, so we're going to double whatever value we get in there. So if you throw in some numbers, if I actually look at those large cylinders, I'm given a diameter of 12, so that means the radius is going to be 6. The 6.4 number, well, that's going to be our height. Okay, so I've got all the information needed, so let's go throw it all in here. So 2 pi, radius of 6, plus 2 pi, radius 6 again. Height is 6.4. So all of that will take care of the one cylinder. So we'll double that number because we've got 2. And that number works out to be 934.938 centimeters squared. Okay, so that takes care of the surface area in full for those two larger cylinders, not subtracting the parts that are overlapped yet. We'll do that at the end. Okay, next thing we'll do is find the area. I'll keep this color coded, so let's find a new color. Area of the small or skinny cylinder, however you want to organize this. Okay, the small cylinder in the center. That's not the same blue, but it's okay. This will be a rainbow mismatch. Small cylinder, okay. So our surface area is 2 pi r squared plus 2 pi r h, the exact same formula. Doesn't need to get doubled because there's only one of those types. There's only one cylinder that looks like that. So 2 pi radius. Well, the diameter is 2.5, so the radius is 1 1/4. There's my radius. Height is 14.8. So 2 pi 1.25 squared plus 2 pi 1.25, and I'm going to run out of room. Actually, let's move this line. Perfect. I'll go there. And the height we said 14.8, straight from the picture. So the surface area of that small cylinder in the center, 126.056 centimeters squared. So you notice I'm choosing not to round here partway through because we're going to need to take a couple extra decimal places just so I get the most exact answer at the end. Because if I round at each step, then I'm continuously introducing a rounding error. So we'll just save all the rounding for the end. So I took a couple of extra decimal places here to avoid that. Now we got to talk about the parts that are not exposed. So the areas not exposed, that's going to be our 4 overlapping circles, 2 from each side where that skinny cylinder meets the ends. Think of it like a dumbbell, right? A weight, where the weights are on the ends and the handle in the middle. Okay, so we're going to have to take out 4 total circles. Okay, so the area of one circle, well, that's pi r squared, but then we'll multiply by 4 because there are 4 identical circles. So pi, the radius of that circle, 1.25, we'll square it. That'll get us one of them. Multiply it by 4. Again, like I said, for all 4 circles, 2 from each side. So our total area is 19.635 centimeters squared. So we've done the hard part, broken down that composite object into its pieces, found each of them individually. Now we'll find the total. And then we're done. So our total area is going to be, add everything up, so 934.938 centimeters squared plus 126.056 centimeters squared, and then we'll take out the 19.636 centimeters squared because, again, that surface technically is not there, not exposed to air. Don't need to count it. And in total, and if you subtract all those things, add them together, and then round at the same time, what you'll end up with, if you go to the nearest whole number, 1,041 centimeters squared. So I know it doesn't say where to round to, so I just made a choice. Whole number is usually easier. Okay, so save all the rounding for the very last step, and there you have it. There you can do surface area and volume of composite objects. If we were to find the volume of this object, it'd be much easier because we could find the volume of all the pieces and then just add. Didn't have to worry about things not being exposed. So I hope that made this a little bit easier for you. And that'll essentially be the end of surface area and volume. So the next time we'll check back in here, we'll start to look at linear equations and really get into lines and graphs and all that sort of stuff. So just remember to check back for those ones. So until next time, everybody take care, and we'll see you then.